Okay, so I'll start if everybody's okay. So this is the introduction for the course Theory and Practice of Finite Element Methods. So this course is thought as a course which is joined between the Master in High Performance Computing for practical part and the PhD in Analysis, Modeling, and Applications. And these are the web pages of the various courses that are involved in this type in this course in practice. So the course objectives are to go from a very simple finite element solution, like the one that you can actually find on the tutorials online using Python and Phoenix, for example. This is the type of solution you would find to solve a Poisson problem on a square, for example, to something which is much more complicated, like the one that you see here. So this is a solution of a fluid structure interaction problem that has been computed together with Michał Dukowski, which is a PhD student at the Institute of Fundamental Technological Research in Poland. And this simulation here was run on actually a few nodes, just 2 nodes with 48 CPUs each. And it took, I would say, a couple of hours to run the simulations and a couple of hours to do the analysis. In order to be able to do this, you have to create very efficient numerical solvers for partial differential equations. And this is the goal of let's say, the practical part of the course, while the goal of the theoretical part of the course is to study the theory that is behind all of these 2 things. So this is basically 2 parallel parts. On Tuesdays, I will discuss about theory of finite elements, and this is what's going to be going on today right after my 10 minutes presentations. And on Thursdays, I'm going to do practice of finite elements. This is a 20 plus 20 hour course. So if you want, as an MHPC student, you can follow the second part, which is practice of finite elements, and it's going to go on Thursdays. Sometimes there's going to be a shift between afternoon and mornings. All lectures are recorded, so if you cannot attend in person, you can actually watch the lectures live. And the main idea behind the course is the following. So what I will be doing is a theory of finite element methods that is tailored to PhD students that want to do a career in numerical analysis and in partial differential equations and solving partial differential equation by finite element methods. This is going to be very in-depth and it's going to tackle all of the details that are required for you to understand most of the papers that you find on the literature on finite element methods. And in practice, this is going to be allowing you to solve serial problems in various flavors, and then do conversion tests, do vector and mixed problems, do local adaptivity, and then we will treat parallelization at the very end of the course, because this is going to be a course that builds up a lot of infrastructure before you can actually solve things. And the reason why we build up a lot of infrastructure is because what we want to do here is learn the tools, the techniques, and the best practices that are used in finite element methods in modern techniques. So you'll learn advanced finite element theory, how to use modern C++ IDEs to build and debug your codes, how to use a large finite element library to solve complex PDE problems, how to properly document your code using Doxygen, how to use Git workflows to develop your applications, and how to leverage GitHub Actions, Google Tests, Docker images to test and deploy your application, and how hybrid parallelization works in real-life finite element application codes. And this is exactly the goal that we would like to have. The outcome of the course is you'll be able to produce your own finite element application, which is based on the library that I've contributed in developing for the last 10 years, which is called Youll 2. And this solves a PDE of interest to you. So this is going to be, we will build a project that is interesting for you, or we will try to build a project that's interesting for you on adaptively refined grids in parallel. And this will use modern version control tools. It will be tested automatically every time you push a commit or open a pull request. And it's going to be documented using Doxygen, and its web page is going to be updated whenever you deploy your code or whenever you merge a new master branch to a new branch to your master branch. So the prerequisites are, for the theory, you will need some knowledge of sublet spaces. So linear operators, Banach, and Little spaces, duality are going to be given for granted. And there are many courses at CISA that actually talk about this, and I think you have followed some of those courses. You will need at least 1 elementary course of numerical analysis. And the reason why you need that is because you'll need to know about quadrature formulas, interpolation, Taylor expansions, and some of this elementary stuff. So if you follow the first part of the course in the Master in High Performance Computing, or the course for the PhD students on elementary numerical analysis, this is exactly what we're going to be using. And in terms for the practice, for the first few lectures at least, you'll need a machine with Visual Studio Code installed, and we require a C++11 compiler, or alternatively Docker, to have everything pre-built and working within Visual Studio Code. So Visual Studio Code is a IDE which actually is cross-platform. So I'm going to be able to work with you if you are on Windows, on Mac, or on Linux, as long as you have Docker installed and Visual Studio Code installed. Then the setup time is going to be short for the first week. At some point in the future, we will be compiling everything from ourselves, and we will be doing all of this stuff for ourselves. But at the moment, this is not going to be required. So we'll work with pre-compiled libraries and pre-made images on Docker. And you will need a GitHub account. So more info you can find on the course pages. I'll share this PDF with you guys, so you'll have access to all of these slides. And the official course page is the one that is present at the beginning here. And this is where you'll find up-to-date information about time and dates of the course, about the course being online or live. Closed classroom, course classroom is going to be done on GitHub. So there's a classroom, GitHub Classroom code that is open and will be filled with theories and with assignments and exercises. And all the slides, the notes, the materials, and the codes will be available on the GitHub account that you see here, on the GitHub repository that you see here. And the recordings are available on YouTube on a playlist on my channel, which you can access through this link. If you need anything, you can send me an email and we can arrange for something. So I will now start with the introduction of the first lecture of the course, and I will leave the ground to the other professors of MHPC to present their course, while I will keep teaching the first introductory lecture of theory to the students of the PhD on the other Zoom. So let me just stop the sharing for a second, and I'll give back control to Alberto and Rachele. You can go forward. Okay, so now I have finished the presentation for the students of the Master in High Performance Computing, and I will concentrate on the first part of the course. So I see that we have a few students here. For the first few lectures, I think this is going to be entirely online for organizational issues. And as soon as we realized if it's possible to move it on a mixed way, I will try to go on the mixed way, but this may not be something that we do right away. So let me just share my notes, and let me share my screen. This should work. I've tested it before. Okay. You should see the first slide of my presentation. So keep in mind that I will start recording now. So if you don't want your face to be present in the recording, do not turn on your camera. Okay. Okay, so the introduction of the presentation was, I think, quite self-explanatory. So let me just go directly to discuss with you exactly what this course is going to talk about in the theory part. And let's start with the actual course itself. So this is a course which is thought for PhD students. So in principle, the theoretical part of the course should give you all the instruments and the tools that you need if you want to use finite elements in your day-to-day research or in your PhD projects. So the idea here is that this is basically going to build on top of what Professor Cangiani has already done in his course. So I see that most of you have already followed the course by Professor Andrea Cangiani, and if not, I will give a very short. So the course is self-contained, so it's not necessary to have the background of Professor Andrea Cangiani for this course, the course of Professor Andrea Cangiani for this course. However, it will be really helpful if you do have a background on functional analysis, because I'm not going to go into the details of all of those things. So for example, I'm going to give for granted that you know what a soft knot is, and I'm going to give for granted that you know what a Hilbert space is, and what scalar products in Hilbert spaces are, and what is a duality, what is the norm, the operatorial norm of an operator, and so on and so forth. So first of all, let me ask if audio is okay and if the quality of the screen is okay. So is everything fine with you guys?
Yes.
Okay, very good. So somebody is out there listening to what I'm saying. Very good. So what are finite elements? So finite elements is a very, very wide class of problems in a certain sense. So it's a technique that is used to solve partial differential equations. So the idea here is that you have a domain. Let's say that we call this object here domain omega. And this object is a subset of a set, which is usually RD. So hopefully my face is not going to be right on top of the writing. So I'll try to move this around a little bit so that you can actually see better. Yes. Okay, so the idea here is that the subject of finite element methods is to find an approximation for a function, which is usually a function defined on domain omega in RD. So these are functional approximations. And the idea here is that we have for example, let's say here, the thing that we would like to solve here is U is the displacement, vertical displacement. Okay. Of every point of this object that you see here. So this is a complicated object in 3 dimensions, and we would like to construct a field that describes the vertical displacement of a elastic material. Okay, when subject to a force, to an external force. Okay. Now, this problem, as it is said, so in this way, tells that the unknowns of our equations are functions U, that represent a value or vector value or something complicated at each point of the material that you're looking to study. So this is an example of a problem. So of course, there's many other problems that you can solve, but the principle is that the unknowns of the problem is a function U, and the way to solve this problem is to set the problem in a variational formation. Okay? So the idea here is that U is an unknown, and to a force F, so the force F is the data that we know, and a lot of the problems that look like this one can be formulated in variational principles and can be formulated in symbol of spaces and in Hilbert spaces. So the idea here, so keep in mind that what I'm going to write here has the prototypical problem of partial differential equations is the following. So we assume you have a domain omega. Now this is the potato-shaped domain, typically potato-shaped domain. And the potato-shaped domain is a representation, let's say, of the piece that we had on the other slide. And this potato-shaped domain is omega, and we assume that omega is Lipschitz bounded and subset of RD. Now, for our course, D is going to be equal to 1, 2, or 3, but there are problems in for example, in astroparticle problems in which you have not just spatial dynamics, you can also have time, so this could be 4, or you could also have other things like, for example, frequency domains or other types of problems. So this is, you can get arbitrarily complicated, but for the purpose of this course, we are going to concentrate only for the equal 1, 2, or 3. And the prototypical problem that we're going to solve is an elliptic problem. And we write the elliptic problem in the following way. So the idea here is that we want to solve a partial differential equations of the type Laplacian of u equal f in the domain omega, and u equals 0 on the boundary of omega. So this is our prototypical example of a problem that describes exactly the type of problem that I've shown you before. So, for example, the vertical deformation of piece of metal that is shaped into a mechanisms or into a gear, and it's loaded with forces. Okay, so this is the prototypical problem. And in this picture, the boundary of omega here is locally the image of a Lipschitz functions. So this is what omega Lipschitz means. Okay, so if you take the part of the domain omega, there is a theorem that tells you that you can, the implicit function theory that you can actually find a local Cartesian, a local frame of references for which the boundary of the domain omega is the image of a Lipschitz function. This is what the term Lipschitz means in this case. For these types of problems, the principle is that the classical solutions of these equations require a lot more regularity than what it's usually required by the variational formulation. So the idea here is that this problem is formulated in weak form. Now, when I say in weak form, what it means? Well, you can interpret this in several different ways. So interpreting it in several different ways means that you rewrite the minus the Laplacian operator is seen as a weak derivative operator on a Hilbert space. Okay, so what we are assuming here is that we replace the definition of the Laplacian as we normally know it. So the Laplacian would be, so the classical definition would be the following. Laplacian minus Laplacian of u is defined as minus the sum of the second derivative of u with respect to xi with I that goes from 1 to d, the xi square. Okay, so this is what the classical derivative is for these types of problems. Of course, if you want to have a solution in the classical sense, then there's a lot of restrictions you have to ensure. So, for example, the boundary of the domain omega cannot be Lipschitz. It has to be smooth, at least a C2 boundary. F has to be at least continuous. Then if you have this, Laplacian of u might be a C2 function. So this is a complicated settings in which these are formulated. So typically, what one does in this particular case is to reformulate the problem where the Laplacian of u minus the Laplacian is interpreted weakly. So I see minus the Laplacian, and I will give this guy as a operator A. As an operator A that goes from a space V into its dual space, V prime, where V is Hilbert. Okay. And now we will try to understand where this actually makes sense. Okay, so it's interpreted weakly. It means that instead of writing the strong form of the derivatives here, one writes here at this stage, one replaces the second derivative that you see here with the second weak derivative. Okay. Now, writing this with the second weak derivative has several effects. So the first effect is that you can actually see the problem as a variational problem. And the simplest way to proceed in this particular case is by proceeding with the notation that I've written here. So that the way that I will do this from now on is the following. So I write the problem as AU equal F in the space V prime. Okay. Now this, I hope that this has a meaning for you guys. So if this has a meaning for you guys, then I can go very quickly. Otherwise, we have to specify what this actually means. So AU equal F in V prime is equivalent to writing, so same thing, as taking the duality product between AU and V and F and V for any V in capital V. Okay, so far I haven't specified anything about what space I'm looking at and where I'm looking at this problem. The principle behind everything that I'm trying to do at the moment is the following. So I'm replacing the Laplacian with a weaker operator. And we know that this is a linear operator because of the linearity of the derivatives and the linearity of the weak derivatives. And now I would like to understand what is the space V where this linear operator is well defined, what is the space V prime where this linear operator is well defined, and how I can write my Laplacian of U equal F into AU equal capital F in V prime and interpret this as this writing over here. So if you have questions, stop me. So if there is something which is unclear so far, stop me. I think you have seen already this in previous course, so I'm not going to go into too many details of these types of things, but the principle with which one actually constructs these operators is very simple. Okay, so let's try to construct this linear operator. So let's first assume that you know what this notation means. And I hope you know what this actually notation means. Okay, so if I'm saying that A is a linear operator that goes from V to the dual space V prime, it means that A takes a function U and returns to you something that is interpreted as a linear operator on the space V. How do I interpret AU as a linear operator on the space V? Well, this is exactly the meaning of the duality brackets that I'm seeing here. So the principle here is that I am defining, in this particular case, the duality as the integral of AU V on the domain omega. So a linear operator, so this notation is used a lot, and it's given for granted a lot. So let me just remind you how I'm using this notation here so that we can all be on the same page. So I'm using this notation to represent a linear operator, a U, is a linear operator on the space capital V. And I'm saying that these objects, when I apply the duality of these objects to V, you can also find this often in the literature as AU of V, a linear operator. AU of V belongs to R, and AU is linear. Linear functional from V with values in R. And it's defined, well, from the way that we define this here, the linear functional from values in V in R is exactly taking the integral of AU times V, in this particular case, in omega. And this is formally written in this way. And we will see that if you apply the definitions of the weak derivatives as they should be, then the weak form of the problem can be written as AUV is defined as the integral on omega of the gradient of U, gradient of V. And this is what usually you see on courses of finite elements, where they explain to you that this is the weak form of the Laplacian of U times V. There's several ways to get to this case, right? And of course, you can see this as where all the gradients that appear here are considered weak gradients, and all the derivatives that appear here are considered the weak derivatives. The Laplacian of U is often seen as minus the divergence, or so minus the Laplacian of U is often seen as minus the divergence of the gradient of U. So you can recover this expression simply by saying, I take minus the Laplacian of U, I multiply this with the test function V, which is smooth enough, integrate on the domain omega, and what I get is I can integrate by parts this, and I would obtain the gradient of U, gradient of V, minus the derivative of U along the normal direction, integrated on the boundary of omega, times V on the omega, and then one chooses the space, the functional space, in such a way that the term that you see here on the right-hand side disappears. And this is exactly how the weak derivatives are defined, if you recall. So weak derivatives are defined in such a way that they make sense by integration by parts on every, well, when you test them against every function V, which is C infinity with compact support on the domain omega, so that the terms on the boundary that contains the V disappears, and you are left only with this term over here, which is the variational formulation of the Laplacian operator applied to a function test, to a test function V. So I'm just giving you here a very brief recap of what you should have seen in the course by Andrea Cangiani, or in the course on the numerical analysis course that we did at the first part of the semester, if you follow that part of the course. Okay, so the idea here is that now we would like to formalize this, and we would like to exploit, to find a way to approximate these problems in a computer. And so the course is going to be designed throughout the idea of how to implement this correctly in a computer code. So how to actually build objects that perform this operation over here, and to see how these relate actually to standard numerical approximation procedures that you might know from the past. So let me just spoil this from the beginning. So the first part, so the typical procedure in FEM is replace the space V. I haven't said yet what the space V is, but it's a Hilbert space in this particular discussion, which is infinite dimensional. and Hilbert with VH, and this is a VH which is finite dimensional. Okay. And included, or it's a subspace of capital V. If I do the procedure, what happens is that the writing that we had before, there was AU equal F. This is usually written in V prime, becomes, I simply restrict the same operator on a smaller space. So I write this as A UH equal F. Instead of V prime, I write here V prime H. Okay. And now I will be trying to write explicitly what it means to do this passage. So this passage is the following, is usually written in the following way, right? So the fact that VH is finite dimensional, this implies that we can express the space VH as a linear combination of linearly independent basis functions, and the number of basis functions depend on the dimension of the finite dimensional space. So I can write VH as the span. Now I will write consistently basis functions with the lower index here, and you will see clearly why I do this in a few seconds. If they are basis functions of the primal space, okay. And if it's finite dimensional, then every function UH can be written as the sum of UI VI. And if I look at this writing, let me be more precise. There exists a unique vector UI for I that goes from 1 to n that belongs to Rn, such that UH evaluated at the point X can be written as UI VI of X, and here sum is implied when repeating indices in opposite positions. So what do I mean by repeating indices in opposite positions? Well, coefficients here, I put the indices on the top left, while basis functions here, I put the indices on the bottom right. Okay, so top left, bottom right, these indices are opposite to each other. So if they repeat, they sum. This is useful, and you will see why this is useful in a second. Whenever I use this type of notations, what happens is the following. Every function UH can be written as a linear combination of the basis functions and the coefficients. And in particular, since the space is finite dimensional and the bases are linearly independent, we know that there exists a unique object that does this. Okay? There's a unique set of UIs that univocally represents our basis functions. The fact that this is true tells you that any finite dimensional space is homomorphic to Rn. So we can always represent any finite dimensional space as a vector in Rn. And this is going to be the goal of finite element methods. The finite element method is to try to represent infinite dimensional problems in the space, in a generic space, capital V, as finite dimensional problems, but they do it in using the space VH, or choosing the space VH, or constructing the space VH in such a way that approximation properties are well satisfied. So the idea here is that when I write this in VH prime, so what this really means, that doesn't really mean much if you don't contextualize this. So this actually is equivalent to saying that for every VH, you can write this equation in capital VH. Okay, so this writing, so saying that AUH equal F in VH prime is the same as asking that A of UH tested against VH is equal to F time tested against VH for every VH in capital VH. Okay. And now, why is this useful? Well, this is useful for the following reason. It's useful because since now we can put together what we have here on the right and what we have here on the left, and instead of using arbitrary functions that we have here, what we do is we use the basis functions that we have there. So the problem is equivalent to writing A of Vj uj with the notations that we wrote there times Vi equal F Vi. And now this is for I that goes from 1 to n. And in other words, this is now equivalent, if you look at this from the mathematical point of view, it's equivalent to writing a matrix A in vector U. Let me write this in this way, just to differentiate between the operator A that we had before and the operator F that we have here. And you can actually write this explicitly as A, I, J, Uj equal Fi. And now we can give names to these guys, and we can actually write explicitly what these guys are. So A, capital Aij is simply the operator A applied to Vj tested against Vi, while Fi is simply F tested against Vi. And now, if you look at this equation that you have here is a linear system. Okay, so this is a linear system of equations. Okay, and we would like to understand first how to solve this equation, how to write these equations, how to assemble this matrix, and how to visualize the output, and all sorts of things that appear that are required for you to understand this part. The linear system of equations you can try to solve if and only if you know that this solution, that a solution to the system exists. And now comes in the theoretical part of it. So now the theoretical part of it says that if you have the conditions that the operator capital A, which is the one that appears here, which is the one that we are applying to basis functions Bj and Vi, satisfies certain conditions, and we will discuss about these conditions now, then automatically the matrix A, capital Aij here is going to be invertible, and we can find a unique solution to these problems. Okay, so we went from a infinite dimensional operator, A, that takes objects in a linear space V, capital V, and returns a linear operator on the same space. So that's the definition of our operator A that we wrote here, is a linear operator that takes objects in the space V and returns linear operators in the space V. Okay, so linear operators in the space V are exactly elements of the dual of V. And what we have shown here is that if you look at the problem from the finite dimensional point of view, the only thing that you actually need to do here is to construct a good finite dimensional space, VH, that approximates well the space capital V. So V and VH are the guys that we want to look at. And a lot of the part of the course is going to be how to construct the space VH, how to make sure that it approximates properly the space capital V, and how to implement all of the things that I've written here so far. Okay, so let's start by putting some dots on the eyes. Right, so let's start with the correct definitions. First definitions over here, and this is Lax Milgram lemma. You should have seen this already. However, what I'm going to do here is I'm going to prove the Lax Milgram lemma not for the simplified case of symmetric operators, but for the general case of non-symmetric operators. Okay, so Lax Milgram lemma, let's assume V is Hilbert with norm indicated by this. So I'm not writing anything here. If you prefer, you can think of this as the V norm, but I'm not writing it just not to have too much noise on the notations here. Okay, so V is Hilbert with norm that, and assume that A is a bilinear operator on V. So I take A, takes pairs of functions in the space capital V and returns to us a value in R. And we assume that A of U V is defined as the operator capital A applied to U evaluated on the function V. Okay, so this guy, a U, is an object of V prime. When I evaluate this object of V prime as a on the test function V, I get a real number. And if I look at A is a linear operator in U. And so if I look at this object as a operator on pairs, U, V, then the resulting operator that I have over here is a bilinear operator. So it's linear in both entries, both in U and in V. Okay. So the two assumptions that we have here with A of UV is bounded. Now I'll write here norm A, and then we define what this is. Okay. And second assumption that we have is that A of UV, actually, when you apply A to U, this is greater or equal than a constant alpha, norm of U square. And let's say, to understand this better, we move this a little bit downwards, and we say, and assume that there exist alpha in R greater than 0, such that this is satisfied. So this is boundedness, bounded. This is coercive. Okay. So hypothesis of Lax Milgram lemma. V is a Hilbert space, okay, with norm induced by the scalar product in the Hilbert space. And we assume that A is a bilinear operator. Okay, and for what we are discussing now, the bilinear operators that we look at are always going to be in the form of operator capital A applied to U tested against V, which is exactly what we have here. And now the Lax Milgram lemma assumes that there exists a constant alpha that we call the coercivity constant. And this constant has to be strictly positive. And it's such that if you take A and you apply to two functions that are the same functions in the space capital V, then what you get is that the number that you get has to be strictly greater than alpha, where greater or equal than alpha norm of U squared, where alpha, however, is a positive number, strictly positive number. Okay. Okay, so let's see what then this means. Then Lax Milgram lemma says that for any f in the space V prime, so for any linear, for any object of the dual, so for any linear operator on the space V, that exists a unique U in V such that A of UV, which is equal to little a of UV, is equal to FV, which is often written as F of V for any V in capital V. And moreover, we also have that the norm of U is controlled by 1 over alpha norm of F in the dual space. Okay. So let me just recap here. What's the norm of F in the dual space? So this is a dual norm of F. This is defined as the supremum for any V in the space capital V, which is non-zero, of F of V divided by the norm of V, which is often written with the duality product. So according to what's the best way that you prefer, this can be written as F, comma V. Okay. So far, so good. Any questions? Okay, I'm taking that as a no, there are no questions. Okay, now, how do we prove this? So first of all, we would like to prove that there exists a unique solution for any function which is in the dual space V prime. We would like to find that there exists a unique solution in the space capital V. So if in the symmetric case, you can show that this is equivalent to resolving a minimization problem. In the non-symmetric case, this is no longer the case. So we have to play a little bit more, we have to play a little bit harder to get this result. So how do we get the result in the general case? So in the general case, the idea is to try to construct a fixed point iteration and to use fixed point theorems to get a unique solution of the problem. To rewrite the system as a fixed point iterations, we first need one intermediate result, and an intermediate result is the following, and is Ritz representation theorem. Hence the name, Ritz-Galerkin methods. So Ritz representation theorem. So for any function capital F in V prime, there exists a unique function little f in V, such that now we basically write the duality representation of capital F, and we exploit for this the scalar product of the Hilbert space, right? So this is such that FV scalar product induced by the Hilbert space V. I'll write this explicitly here because this is usually, if I don't write anything, usually the parentheses here indicate the L2 scalar product, but this is not necessarily the case in this particular example. And this is equal to capital FV for any V in capital V, okay? So the Ritz representation theorem says that there exists a unique function f that satisfies this property. And moreover, if you take the norm of f in V, this is exactly equal to the norm of f measured with the dual norm, okay? And the Ritz representation theorem can be we call tau the objects that go from V prime to V, the operator or the Ritz operator that maps elements of V prime to their representation in V. Okay, so Ritz representation theorem in Hilbert spaces tells you that if you have a scalar product, if you have defined a duality product, then you can identify elements in the dual space with elements in the primal space by this projection that you see here. Okay, simply solving this problem in which you do the scalar product between f and any possible function v, then and making sure that these are equal to all possible projections in capital F with respect to the function v, you get a way to represent every function in the dual space with functions in the primal space. Why is this useful? Well, this is useful as an intermediate result for the following. I'm not going to prove this result. I'm going to use this result. So this is useful because we can then use it to define a fixed point in V, such that a fixed point problem in V. Now, the idea is the following. I would like to construct a function t, maybe depending on a parameter that we will call rho, of u, such that t rho of u equal to u if and only if u is solution to a u equal f in V prime, which is the same as writing a u v equal fv for any v in capital V. Okay? Is it clear what we are trying to do? We would like to construct such an object. Now, and the question is here, I mean, of course, I would like to be able to do this. We could take a u minus f and consider morally plus u minus u and write this as a simple fixed point problem that has a solution whenever you have u, which is or maybe with a minus sign here would be better. Minus sign here, it's better. This would be what I would like to do in a certain sense. So I would like to sum and subtract u to this object on the left-hand side, so that when you have that u is a solution of this problem, you can simplify the two things that appear here on the right, and you would get that minus a u is equal to f on the left. However, I cannot do this because I would be comparing apples and pears, because this object over here belongs to v prime, while this object belongs to v. And so the idea is, well, let's try to do the same thing with an object that belongs to v instead of v prime. And so the principle behind the construction of such an operator is exactly the following. So instead of saying this guy, what we do is we try to write minus rho tau, where tau is the Ritz operator that we just defined. Okay, and now if you look at this guy here can be written as t rho of u, which is u minus rho tau au minus f. Now by construction, t rho of u equal u, a fixed point, if u is such that t rho of u is equal to u, then au is equal to f by construction. And so this is exactly what we would like to understand. And let's try to figure out if we can show, in some sense, that this t rho of u is admits a fixed point. So if it admits a fixed point, then we are good to go. And in order to show that this admits a fixed point, the idea is to choose the parameter rho that I put in front of this guy here, and now you'll understand why I put this in front of me here, is to choose it in such a way that when I perform the fixed point iteration, and I start with an arbitrary value of u, of a beginning u, which is input from 0, and I get a contraction, and I can apply this iteratively and get to a convergence. So the idea is that search for rho such that t rho is a contraction. Okay, so what does it mean that t rho is a contraction? Well, it means if I say t rho of u1 minus t rho of u2 in norm. Now, this is the v norm because t rho returns to you something that goes, I didn't write it anywhere, but fixed point problem in v where t rho goes from v into itself, and we would like to find a fixed point of this guy. So t rho of u1 minus t rho of u2 has to be smaller or equal than L, norm of u1 minus u2, okay, where L is a real number smaller than 1 such that this is satisfied. I mean, it's clear that if this is satisfied, then well, why is this a good thing? Well, this is a good thing because then you can start from u0 arbitrary and define uk plus 1 equal t rho of uk And once you have done this, what you can say is that UK plus 1 minus UK in norm is going to be smaller or equal, since UK plus 1 is T rho of UK. This is exactly actually equal to T of UK minus T of UK minus 1. And by construction, this is going to be smaller or equal than L, norm UK minus UK minus 1. And now if I keep going and I go to the first iteration, this is telling you that UK minus 1 minus UK is smaller or equal than L to the power K or K minus 1. So I think it's probably K minus 1. Norm of U0, sorry, let me write this as T rho of U0 minus U0. Okay. And now, of course, if TK is L is such that this goes to 0, so if L to the power K minus 1 goes to 0, which means L is strictly smaller than 1, then what I'm saying is that this is a Cauchy sequence. And if it's a Cauchy sequence, it admits that exists U tilde such that T rho of U, or actually, let's not call it tilde, that exists a U such that T rho of U is equal to U. And then, of course, if you have that this is a contraction, you can also show that this is actually unique. And the reason why you can show that this is unique is it is unique. And because if it was not unique, if not, then what we would have is the following. We would have U minus U. This should be strictly smaller or equal than T of U tilde. Sorry. If not, then this is T of U tilde minus T of U, which we know is smaller or equal than L U tilde minus U, but this is a contradiction. Because I'm saying that the norm of U tilde minus U is strictly smaller than the norm of U tilde minus U, because L is strictly smaller than 1. Okay, so this proves uniqueness. So U is unique. So this is what we would like to do. We would like to show that this T rho is actually a contraction, or there exists at least a rho for which this is a contraction. And now, how do we prove this? The simplest way, the simplest idea to proceed is to actually use the definition of this T rho. So given two functions, T1, U1 minus U2, I just copy this, okay? And I paste it here. And now what I would like to do is I would like to take the scalar product of this guy with respect to U1 minus U2. And I take the scalar product in V. If I take T rho U1 minus T rho of U2, then by construction, this is exactly defined as we have U1 minus U2, these two guys, minus tau rho, everything is linear, so you can have tau rho A applied to U1 minus U2, and the F disappears. When I apply this T rho to U1 and T rho to U2 and subtract them, the terms with the F that we have here, they are the same terms. So when I apply this to two things and subtract, I would get two different, I would get that the F disappears. Okay, so all of this game here is to remove the F's basically. And then I test this against U1 minus U2 in the scalar products of the space capital V. Okay? If I do this, by definition of the scalar product and by definition of the norms, this is exactly equal to the norm of U1 minus U2 squared. And on the other side, I have minus rho square, well, sorry, I have minus tau, so minus rho and the scalar product of tau A applied to U1 minus U2, comma, U1 minus U2. And this is in the scalar product of V. And now we recall what this actually means. And this is exactly, if I keep going in this direction, so I just rewrite this with a different notation, right? This is minus rho, so rho is a number here. And what we are saying here is that this object is the same as writing A of U1 minus U2, comma, U1 minus U2. And what I'm saying here is that this terms U1 minus U2 squared by okay, and so what I forgot to write on the right hand side here was, so this is exactly T1 T rho U1 minus T rho U2. And now what I would like to show is that these two, that this term that I've applied here, I want to understand whether this is actually smaller or equal than U1 minus U2 in norm, okay? So if this is true, I have to find out that there's a contraction scheme over there, which will tell me exactly that this is a smaller or equal, strictly smaller than 1. Okay. So when I plug this in with the scalar product between U1 and U2, what I obtain is so let me write. So this part over here, it's the second part of the thing that I need to show, because I'm missing still the first part, which is the first part that I want to show, is that I would like to show that T rho of U1 minus T rho of U2 is strictly smaller or equal than L norm of U1 minus norm of U2. Okay, so this is what I wanted to show. And now the thing that I did here was to take the scalar product between T rho of U1, T rho of U2 in the norm of U1, while I could have done directly here the computation of the norm of this case. Okay, so since this is what I wanted to show, let me go back here. Sorry, I mixed two ways of proving this, and now I think it's better to go back to the one that I know best. So let me look at the second at the square of the norm of these guys. By the square of the norm of these guys, I have essentially that this is exactly equal to the square of the norm of U1 minus U2, as we said before, minus rho tau A of U1 minus U2. Oops. A of U1 minus U2. Okay, and now I wanted to have this square. And I want to understand what happens if I take the square of these guys and to see whether I can reconstruct the equations that I had before. So forget about, for a second, forget about what I wrote here. I might need this later on, but what I want to start from is this, which is much simpler to understand. So I start with the square of this norm, T raw U1 minus T raw U2, and I expand this explicitly. So I get here U1 minus U2 square. And now at this point, I get here plus rho square tau A of U1 minus U2 norm square. Okay, and then I get the double product between these two guys. So if I take the scalar product of U1 minus U2 minus rho A U1 minus U2 to get the norm square, I would get the double product here with the minus sign. Which is here. And now you get 2 rho, and the product is tau A U1 minus U2 U1 minus U2. I'm sure you can also prove it going on the other direction, going on the other way, but this is, I think this is a little bit simpler. Now, if I look at these guys, this guy over here, what I am actually showing here is that what I want to show is this guy over here is strictly smaller than L times the norm of U1 minus U2 square. Okay, so this is what I would like to show with L strictly smaller than 1. Okay, so I have the square of T raw U square, but maybe there should have been a square here if I do it this way. So this is L square with L strictly smaller than 1. And if I look at it in this way, then what I have here, I would like to now try to figure out if I can proceed with what we know about this inequality in terms of the Lax Milgram lemma hypothesis. So let's try to take a look at this. And the thing that I wanted to point out at this point is this is where I got confused, is if you have 2 raw with a minus in front, 2 raw scalar product between tau and A U1 minus U2, U1 minus U2, okay? This term over here that we have is exactly identical by Ritz representation theorem to minus 2 rho. And now here we have the duality. And since tau is there, this becomes A applied to U1 minus U2 measured on U1 minus U2. Okay. And now what we know about this object over here is that by duality, the term that you have inside is greater or equal than alpha, the norm of U1 minus U2 square. Okay. And now this is with the sign, with the positive sign. So this is greater or equal than alpha U1 minus U2. So since you have a minus in front, you know that this is smaller or equal than alpha U1 minus U2 square. Okay, so since it's with the correct sign, we can keep going and say U1 minus U2 square plus rho square tau A of U1 minus U2 square. And now we can subtract 2 rho alpha. And here we have norm of U1 minus U2 square. Okay. And the idea here is that this guy alone, we have used so far only coercivity. So here we have used coercivity. And here we would like to use the other property, which is boundedness or continuity of the equation. So I'll simply rewrite it here directly right away. And what I'm saying here is that this is smaller or equal than that. And at this point, what I'm going to do here is I'm going to write this as normal A. And this is the star norm with respect to A. So this is the norm of A as an operator between V and V prime. Okay, it's a linear operator, so this is a bounded norm, and this is the first equation, the first conditions that we have on the boundedness. So we have boundedness here and coercivity used here, and what we have obtained is basically that if you rewrite this from scratch from the beginning, this is tau rho of U1 minus tau rho of U2 square is smaller or equal. Now I can collect in front of this, there's a 1 plus rho square norm of A star minus 2 rho alpha, and then norm of U1 minus U2 square. Okay, now we go to the right point. So this guy over here is our L. And we would like to have this guy over here, we want L to be smaller than 1. If you want L to be smaller than 1, what we need to make sure is that that we choose rho in such a way that this is actually satisfied. So the idea here is that we would like to have -1 smaller or equal than 1 plus rho square A star minus 2 rho alpha or smaller or equal than 1. And now I can tell you already that the one on the left doesn't take you anywhere, because it gives you I mean, you can actually solve these equations. This is a quadratic equation. You can solve this explicitly. The one on the right is simple to solve, and the one on the left is saying difficulties to solve, but I don't remember ever how the things. So this will give you two conditions. So the first conditions that you get on the alpha is you simplify these these ones that you get over here, and you get that rho has to be smaller. Actually, this was L squared. Okay, but so rho has to be smaller than, from the way that I wrote this here, this should be 2 alpha over A star. Okay. If rho is smaller than that, then L is smaller than 1, and there exists a unique solution to fixed point. Okay. And now how do we proceed from here? Well, from here, the next step is to actually show that by using the same properties that we had before, what we need to show is that there is a continuity, that the continuous dependence on the data between the solution and F. And the way to proceed here is to apply directly the fact that so the idea here is to proceed from here. So if I take A of UU by coercivity, what you get here is this is smaller or equal than the norm of U square. And this is exactly identical by construction. Since this is to be valid for any U, this is to be identical to FU. And now, by linearity of the operator F, this is smaller or equal than the norm of F star and the norm of U, which implies, in particular, now let me write this a little on top. This implies that the norm of U is smaller or equal than 1 over alpha, the norm of F in the dual norm. And this only requires the fact that you have cohesivity here and the fact that F is a linear operator in V prime. Questions so far? Okay. Now let's go forward. Let's go forward and let's apply the Galerkin method. The Galerkin method is the following. Since we simply wrote everything, find UH such that A of UH VH is equal to F VH for any VH in capital VH. Since we construct a finite dimensional space VH, which is a subspace of the space capital V with finite dimensions. So this guy here has a finite dimension with respect to the space capital V. Okay, and we want to find an object on this subspace, on the subspace V, that satisfies the same equation when you test it with all the functions on the given subspace. And we know that the exact solution, A of U, satisfies already this for any V in capital VA. But since these are also functions of capital V, then you can apply the same type of equation to the exact solution. And now what the difference between the two is that this comes from an infinite dimensional approximations or for an infinite dimensional problem, while this comes from a finite dimensional problem. And now the idea is, thanks to the way that we wrote problems and thanks to the way that we framed the problem in terms of finite dimensional subspaces, and we framed the problem in terms of variational formulations. What happens here is that you can subtract the two equations, and what you would get is the following. What you get is A of U minus UH tested against VH, and on the right, you get 0. And this is a remarkable property that finite element approximations have, but finite difference approximations don't. So the idea here is that the error that you commit is A orthogonal to capital VH. And this comes from the fact that simply by defining the subspace capital V H as a finite dimensional subspace of capital V. Okay? And this is also known as Sear's lemma. And as a very important, well, not all of this is, so this is part of Sear's lemma. So Sear's lemma is the following, is the application of this with the conditions of Lax Milgram lemma. Okay, so if you now proceed with the Lax Milgram lemma, similarly to what we did at the beginning to find out what was the stability properties, let's try to analyze what happens here with respect to the error. So we say that alpha U minus UH square is certainly smaller or equal than A applied to U minus UH tested against U minus UH. And now what I observe is the following. In this equation here, this thing, so A of U minus UH is equal to 0. Not at all it's equal to 0. Anytime that you take any function, capital VH is equal to 0. So you can add and subtract 0 to this equation, and this will become exactly the same thing. So we will say, we can write exactly the same thing with A U minus UH, U minus VH instead of UH, simply because both of this give rise to something which is equal to 0, and the same is valid here. Okay? And now what I do is I apply the continuity equations. So what I'm saying now at this point, I apply the conditions that A is bilinear and bounded. And now what you obtain here is U minus UH, U minus VH. And this has to be valid for any VH in capital VH. And if you read carefully from left to right, one of these two guys disappears with that guy over there. And what you're left with is the fundamental property of finite element approximations, which is the following. If I take U minus UH, so the error you commit between the exact solution of the continuous problems and the approximate solutions constructed using a finite dimensional subspace, this object is as close as it can get modulo two constants, which is A star here over alpha. It is as close as it can get in the space that you've constructed. So no matter how you construct your space, your finite element approximation with that given space is going to be smaller than a constant, which depends on the problem, and of course depends on the operator that you have there. So for the Poisson operator here, you get 1 if you don't have any constants over there. And here you get 1 as well. And what this is telling you is that the error that you commit in the Hilbert norm is smaller or equal than the infimum that you can commit with any functions v that you have there. Okay? And so the idea of the finite element method and the idea of this course, so the main goal are going to be the following. First, construct VH such that the supremum for any U in capital V of the infimum for any V in capital VH of U minus VH and let me call this the distance between V and VH is small. Okay. Main idea of goal of the course, construct a VH such that you can actually control the distance between these guys. And small, typically, of order h to the power k, where k is an approximation order of the finite dimensional space. Okay. So here, now you understand the meaning of this little h. So it's a parameter that will go to 0. And when it goes to 0, it decreases the error that you make by approximating your finite dimensional space, your infinite dimensional space with a finite dimensional one. And so main idea is to construct the VH such that this is small, to measure the distance between V and VH, and to estimate U minus UH in norm. So those are the two things that are the most important. And then if we get, of course, once you have this, given F and U, find the best possible VH. Okay, so in some sense, the analysis that we have here, this is an a priori analysis, and it gives you the worst estimate, worst case scenario. Okay, so this is worst case. Instead, here, given, so there's a missing N, given F and U, find the best possible VH. This is a posteriori scenario. So this is an a posteriori problem, which means in the first case, I'm simply interested in figuring out a way to approximate all possible problems that are given to me. In the second case, I'm given a problem, a specific problem, and I want to find the best possible approximation space that gives me the best possible results. Okay? So these two are going to be the leitmotif of everything, right? So we are going to be understanding the estimates that come out from here. So we're going to estimate what is the distance between finite dimensional spaces and infinite dimensional spaces. We are going to measure these things and estimate how they go with respect to several norms of the functions U. And then we are going to do this a posteriori error analysis, which is given F and U, or given F and UH, find the best possible VH in such a way that is computable and that is actually implementable in a C++ code. So questions so far? Okay, very good. Now let's try to make life concrete in the one-dimensional case, and let's try to understand exactly how these things work in the 1D case from scratch. Okay, so this is going to be a 15 minutes excursion of how to do this, in 1D. Okay, so 1D. So let's say that omega is the interval 0, 1, and the boundary of omega is the set point 0 and 1. Okay, so what I'm asking here, I'm trying to solve the function minus u prime prime equal f in 0, 1, and u of 0 is equal to u of 1 and is equal to 0 in 0 and 1. Oh, well, actually, I already wrote where. Okay, so this is what I would like to solve. And in weak form, I think you've already seen this in the past, so I'm going very quickly here. In weak form, this is equivalent to asking that the integral between 0 and 1 of u prime v prime is equal to the integral between 0 and 1 of fv for any v in a space. Let me just write the space quickly here. Fv for any v in h10 of 0, 1, where h10 of 0, 1 is the functions v in L2 of 0, 1 such that V prime is in L2 of 0, 1, and V of 0 is equal to V of 1 is equal to 0. So these are functions which are square integrable, such that their derivatives are square integrables, and they are 0 on the two sides of the boundaries. In particular, what we know about these functions is that h10 of 0, 1 is, h10 of 0, 1 is included in C0 of 0, 1. This is for the Sobolev embedding theorems. In particular, if you have a Sobolev space HS, where S is a positive number, and this is going to be included in C0 whenever S is greater than D over 2. Okay, so strictly greater than D over 2. So in this particular case, this is a reminder. So HS is included in C0 for S greater strictly than D over 2. If we were looking for Sobolev spaces with general indices WP space, WSP spaces, they would be D over P. So whenever you have that the derivation order is greater than the dimension divided by the integration order, then the functional space is actually continuous. So for the one-dimensional case, functions are in H10 are continuous. In the two-dimensional case, this is no longer the case. It's just no longer the case in the sense that H1 functions in 2D are not continuous, and you have to be careful a little bit about how you define things. Okay, and now let's try to define how to define VH. And now the question is the following. We set H to be 0, well, to be, it should be B minus A over N, where N is the number of intervals that we want to have. Or if you want to have N, which is the number of points, you can say this to be N plus 1, or if you want N to be the number of dimensions of the systems, this is going to be N plus 1. Okay. So now let's discuss a little bit about this. But for the second, this is going to be 1 over N plus 1. Okay, and I write xi is defined as I times H. Okay, for I that goes from 0 inclusive to N. Inclusive. So if I have I equal to, sorry, to N minus 1 inclusive. Okay. So these are N points. I should have written here N plus 3. Let's put it this way, N plus 3. And this is N minus N minus 3. Okay. Well, you'll understand why I'm writing N plus C and N minus 3 here at this point in a few seconds. Okay, so the idea is the following. So I'm trying to construct a functional space approximations of the interval 0, 1. Okay, and I would like to approximate continuous functions in this space with some piecewise functions. Piecewise linear functions is the simplest possible case. So I have a function, which is this guy over here. Say this is the function u, the exact solution of my problem. And now I would like to approximate these functions using intervals, equispaced interval at the moment. And I would like to write, oh, sorry, the function u for the discussions that I have at the moment has to be equal to 0 on the boundary. So let's pick up again the plot and make the plot correct. So we have here our function u, which is equal to 0 there and 0 there. This is the point 1, 0. This is the point 0, 0. This is x and this is y for the moment. And now what we are saying here is that I construct a equispaced set of points, which are these guys. Okay, and the equispaced set of points that I have here, and I would like to construct an approximation, which is a piecewise linear approximation of my function, and I want to understand whether this is a good idea. Of course, this one, the piecewise linear. This is okay. So now we have UH is this guy, and U is this guy. And I would like to first of all express UH as a linear combinations of UI, VI. Okay, and in a certain sense, I would like this I, and so these I points, to be in a number which is equal to n. Okay, and so this number here. So this is like for once. Let me write this explicitly. I would like to write the sum for I that goes from 1 to n of UI, VI. And we would like to understand exactly how to construct VH, which is a subspace of capital V, which we said at the beginning is H1, 0 of the interval 0, 1. Okay? So the reason why I'm looking for this strange number of points is because there's a 0 here, so I don't want to consider the endpoint. So I only want to consider n interior points. These are n interior points. And I would like to make sure that this object over here makes sense. How do we construct such an approximation function? But there are several ways one can proceed. So the simplest possible way to proceed is to define the basis functions vi according to. So there's two ways to proceed. One is the canonical way, and the other one is the simple way. I don't want to go the simple way this time. I want to go the canonical way. So the canonical way is the following. Bear with me for a second. So we know the dimension of VH. Okay. Let's first define VH and let's say how to construct this object. So let's define VH to be what? These are functions which are C0 of the interval 0, 1, and such that V, when restricted to xi, to the interval xi plus 1, belongs to P1 of xi plus 1 for I equal 0, comma, now this is I plus 1, that's n minus 3. I want to have this equal to 0, and there's a number there that I have to figure out for a second. Let me think for a second to this. and such that v of 0 is equal to v of 1 is equal to 0. So what I'm saying here is that this is a continuous function. It's a piecewise linear function on each interval. And so it looks like exactly like the one that we plotted here in red. So this is a one representative function of that space capital VH. And this, of course, depends on the number of points that I've written here. So the thing here is that I wanted to have these points to be just the interior points. So the size n coincides with the number of interior points, not with the whole number of points. So this would be n plus 2 exterior points, which means you have n plus 1 segments. And so n plus 1 segments, this should have been n plus 1, not n plus 2. And now, when xi is given by this object over here, this is n minus, so I goes from 1 to n. And now, when I'm looking at this xi that goes from 1 to n, I have n interior points plus 0 and 1. In 0 and 1, I don't want to have any freedom to choose because I want to fix the functions to be piecewise, to be constant over there. Okay. So now we don't know the dimensions of VH, and these dimensions are exactly equal to n because it's just the number of interior points. This is the way that I'm saying, this is something that we have to prove. So I can tell you that this is equal to n, and I would like to show you how to construct a basis functions VH, basis functions for capital VH, which is the canonical basis functions. Okay. The way to proceed is usually to choose n functionals in VH prime, called nodal functionals such that they are linearly independent. So in other words, one chooses a base for VH prime. Okay. It will be clear in a second. So let me show you what is the type of basis the one gets. So one chooses n functionals in VH prime called nodal functionals such that they are linearly independent, which is a base for VH prime. And then we construct VI as typically these basis functionals are called nodal functional, and we call them VI belongs to VH prime. Okay, and the I here is on top. And we construct VI such that VI belongs to VH and VJ evaluated on VI, which can also be written as VJ tested against VI is equal to the Kronecker delta, delta JI, which is equal to 1 if I is equal to J, and 0 if I is different from J. And now let's try to figure out exactly how to do this. one simplest choice, but not the unique choice that one has. We choose Vi of x to be the Dirac delta centered on xi. And this is for I that goes from 1 to n. And now, let's try to understand what this is saying. This is saying the following thing. If I take Vi of a function u, this gives me u evaluated on xi, which is equal to the integral between 0 and 1 of the delta, Dirac delta. Oh, so this would be delta of x minus xi, to be precise, x minus xi tested against x in dx, and this by definition is u evaluated on xi. Okay, and now the basis functions as we have constructed, so Vi of x are the so-called hat functions. Now we plot them, and you'll understand exactly where I'm trying to go with this. So we set 0 here, we set 1 here, and now I just plot some of them. I'm assuming that there's only few of them. So this is the first one. This is the second one. And this is the third one. So this is x1, this is x2, this is x3, and this is V1, this is V2, and this is V3. And what I'm saying here is that whenever I look at one of the basis functions, they are defined through the support points that are written here. So x1, x2, and x3, through a basis functions, which are called the nodal basis functions. And those are objects that, given a function which is continuous, will return to you the value of that function on the point xi. And if you look at it in this way, then one can write an operator I that goes from V to VH, which is the so-called interpolation operator for these functions, which is written usually in the following way. And it's V, it's called an operator that to U, it associates, and now you'll see why I like the notation so well, this summation notation so well. It associates to every function U an interpolation where the coefficients of the functions are given by the functions evaluated at the point xi. So this is U evaluated at the point xi, multiplied by Vi, sum for I that goes from 1 to n. And the result is exactly the graph that you have seen before. So if I look at this, I take an arbitrary function that belongs to the space U. I have the 3 points over here. These objects represent U of x1, this is U of x2, and this is U of x3. And I write an object, which is the interpolation between these guys, which is this object that we have here. This is 0, 1. And the properties of this guy is that it interpolates the function u at the point xi, as you give them, x1, x2, and x3. And we know that on each one of the interval, the functions that results from this is a piecewise linear function. Okay? So if I had to look locally at what happens on any interval, so for any interval, there's at most 2 basis functions, one that goes like this, and the other one that goes like this. Okay, so this is from xi to xi plus 1. And of course, this is true for all the interior intervals, but not for the last one, in which we don't have either one or the other one. Okay. Now, I'll stop here for today, and I'm happy to take any questions at the moment. I'll put all of these notes together in the GitHub repository, and I'm available if you have any questions now.
Professor.
Yes.
May I ask a question?
Sure.
Can you explain a little bit more about the contraction T of rho? Because what makes me hard to understand is that it looks like you're looking for a special rho to make the T a contraction. And
yes. So the question here is the following: I don't have a priori a fixed point problem to solve, so I have to construct one. And there's several arbitrary ways to construct contractions. Okay, and the idea here is that I want to construct one particular contraction. Okay, and in order for me to make sure that this is a contraction, I have to make sure that it has the diminishing properties on the norms. And one way to achieve this is, instead of taking directly tau AU minus F, I have to make sure that I don't go too far away from U with respect to the correction, that is the residual correction that I would like to have. And in some sense, the role of rho is to make sure that I don't jump too far away from the starting point when I move towards the fixed point. So it is true, there's no, I mean, this is one possible way to construct a contraction. This is not a contraction for any rho. It's a contraction only if this is satisfied. And this can only be satisfied if you choose rho in a good way. And what I've shown here is that there is one way, at least, in which you can choose rho. And the way in which you can choose rho is the one that I've shown here. You can choose rho such that this is smaller than 1, which means this is the way that you have to choose rho for that to be a contraction. If you don't choose rho smaller than this, then the functions that I wrote might not be a contraction, might be an expansion. So you might not find a unique solution. But since rho is arbitrary, you can choose it as you want. And so this is okay if you choose it positive and if you choose it smaller than 2 alpha over A star. Does that make sense?
Yes, it makes sense. So once you have the contraction, what you are trying to show? Are you trying to show the bottom line of this page? The current page?
So this bottom line of the page, is true independently on the contraction property. The contraction property tells you that whenever you have a function f, which is a function in the dual space, then there exists a unique solution u. Does that make sense? So let me go at the beginning. At the beginning, I showed you here that if you find a T rho, which is a contraction, so the idea here was I want to construct a function u, a fixed point application that we called T rho, such that when u is a fixed point of T rho, then u is also a solution of your original system. And we constructed this in this way, so that whenever T rho of u is exactly equal to u, then this u simplifies and you have that rho tau AU minus F is equal to 0, which means that AU is equal to F. Okay? And so, of course, there could be more than one. So if you had more than one U equal to such that this is satisfied, then you could have non-uniqueness of your solution. What this theorem proves is that if you have a if you have the two conditions that I wrote here at the beginning, so continuity and coercivity, this guarantees that the solution exists and that it is unique. And in order to prove that it is unique, what we did is we wrote contraction, well, we wrote a fixed point iteration, and we showed that depending on a parameter rho, and we showed that if you choose rho appropriately, then this becomes a contraction.
Okay, thank you very much. It's clear now. This means that as long as you find the appropriate rho that works, then
yes.
A equal to I.
Yes. Yes.
Thank you so much.
Exactly. Does that make sense? So there's another condition here on the left that I didn't write, of course. And the condition on the left is the one that comes from this part. Okay. So I only wrote the part that comes from the right part.
It's clear to me now. Thanks a lot. Thank you.
Okay. Any other questions? Okay, then I'll stop broadcasting.